Good day. This is Dr. T, and welcome to the live stream. I'm hoping everything is going well. So today I actually have Q&A for the live stream. So a couple questions on the start with, and then of course feel free to chuck any questions you may have in the chat. There is a bit of a lag, so it may take me a moment or two to read the questions because there is a bit of a lag, and I'm going to have to move my streaming software's window so it's covering up the image from YouTube because I don't think I can take looking at me with that lag. Okay, so the first question up on the list is kind of an inquiry into intellectual property. So in my classes, I'm diving into a little bit of the history of sciences, depending on which class, whether it be the history of chemistry or the history of science in whole. And intellectual property law is something that actually really becomes important for this. So there's this saying that 90% of all scientists who have ever lived are alive. I don't know the validity of the statement, but I'm guessing it's probably pretty legit. Okay, so why does this have to do with what's going on? So the easiest way is to look at the dyeing industry. And the dyeing industry would be, and YouTube is doing something, okay, yeah. I'll deal with that later. The dyeing industry, I'm not talking like morticians or whatnot. I'm talking about people who make your clothes colorful. So, blue. And for this one, of course, this is basically applied chemistry. So you're taking chemicals from various sources. Originally, these would be things like plants, or in the case of purple, the Murex snail, which is, if you want to make something expensive, dye your clothes with ground up sea snail. It's only found off the coast of a few parts of North Africa. I mean, there's a reason purple was purple, and horribly, 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 horribly expensive. Anyways, so this is basically applied chemistry. You got to extract the chemical. You got to get it to stick onto the clothes. In that case, you might, put it on the cloth. It might stick. You might have to use a mordant, which a mordant is a chemical that is, it's going to help your dye stick. So, that's exactly what that is. And so then, you're going to have to do all this, basically science, and it's going to be done by trial and error. Now, in days before intellectual property law and modern, really robust intellectual property law doesn't really become a thing until really the 17th, moving into the 19th century, really the 19th century, where it starts to get like what we would recognize as intellectual property law. So at this point, if I come up with a better way to make a blue shirt, the only way I'm going to make money off of this is to make blue shirts. And so I've got a couple things going on. One, there's only so many blue shirts I can make, and there's other things that have to do with this. So when it comes to blue shirts, then, I'm going to put some effort into making better blue shirts, but I'm not going to make a ton of effort. Now, once you get intellectual property law, this is going to be things like patents, trademarks, etc. But in the case of sciences, we're looking at patents. This now means that if I make a better way of making a blue shirt, then if you learn how I make it, you can't just start making blue shirts. Beforehand, if you learned how I did it, you could just simply copy my blue shirts. And that's a problem. So what I would do, once I get this intellectual property law, is I patent it. So now everyone knows how to make the better blue shirt, but for the next 20 or so years, only I can make it, or I should say, only I can grant permission to make it in my way. And of course, why would I grant permission? Because you hand me a pile of money. And, we can arrange whatever contract we want. I can say, hey, do whatever you want with it. Or we could say, hey, you know what, you make a blue shirt, give me 2% of your profits or something. Whatever contract I'd like to go with, depending on how much value my invention is. This leads to this nice feature where now all of a sudden, knowledge is money. I can sell knowledge. I can monetize this. And once I can monetize this, this is now something to be done for a profit. So now, if I'm a company, I can hire a bunch of people to research stuff. They can research that. I can patent it, and I can either make better stuff, or I can actually, sell that. And thus, this brings in the full force of capitalism. Capitalism has its advantages and disadvantages, but this is one of its advantages. We can bring a ton of money to bear. Whereas in the past, when you're trying to bring money to bear because science is expensive, it was basically the hobbyists or the hobby of the rich. But there's only so many rich people who are bored enough to do science. So, this gets you, instead of, thousands and millions of dollars, this can get you billions, if not trillions of dollars worth of research funding as a society. And thus, intellectual property law unlocks the capitalist markets for doing science. And there's definitely upsides and downsides to this. So don't get me wrong, it's not, a panacea, but it really does change the game and really makes the 19th through modern centuries. Okay, got a couple questions in the chat. Take a look at those real quick. For concept maps, are we taking questions from the focus questions? Greg. Okay, so for my classes, for any of you who are not students who are viewing, I have my students do concept maps, which, plot ideas, connect, basically nouns are bubbles, verbs are lines. And thus by, taking these ideas, putting them on a map, it shows that, hey, we know what we're doing. Therefore, I can say, yes, they know what they're doing, even though I didn't test them necessarily. And it also is a way of studying and a way of, making those connections and helping you remember them. So the answer to the question is going to be, the way I grade them is I look at the questions that are focus questions. So I upload a series of focus questions that go along with each module, basically chapter, but I don't always go with the book. And so those are going to basically be answering those questions. So the map, I've got the map, I look at the focus questions. I'm going to pick 3, maybe 2, but probably 3 of the focus questions for that module. And so that module might have 1 list of focus questions, it might have 3, 4. And of all of the focus questions for that module, I'll pick like 2 or 3, or sometimes I'll squish them together and make kind of a meta question. So if there's 2 questions actually linked together, I might link them. And I try and answer those. And so if they're a good college answer, that's perfect score. If they're an okay answer, or maybe it's a good college answer for 2 or 3 of the ones I was looking for, I'm not looking for all of them, but of the ones I was looking for, maybe some of them are good college answers, others they're an okay answer, but they're not a good college answer. In that case, 80%. If it's well, there's our answers, but this is not really that good, 60%, so a D. This is not that great, but you tried. So for my students who are doing concept maps, make sure you take those focus questions. That's the whole focus of my class. When I build these classes, I start out with a series of questions where if you can answer all of these, you have really done what you need for the class. They're learning objectives, but they're inverted into a form of a question. So where most of the time you see learning objectives, let's see if I can talk, that are phrased like, the student will be able to blank the blank. And that doesn't sound as dirty as it sounds, but you know what I mean? We'll be able to, calculate the square of a circle or something, whatever it happens to be. I'm taking these and reformatting them into a question of saying something like, well, how would you calculate the surface area of a circle? That kind of thing. And so with all these focus questions, the rest of the class is built around that. The lectures are built around that. The PowerPoints are built around that, unless they're straight from the book, in which case I just copied them. Because if you pay for the book, you get to use the PowerPoints. But anyways, so, everything in the class, including these concept maps, is built around these focus questions. So when I'm looking at those maps, I'm looking at the focus questions. Next one for the quiz Thursday. Okay, so this must be a student in my physical science class, which is a survey of physics, chemistry, astronomy, and just an introductory to how science works. So it's a hardcore course. We're covering a lot of content. Quiz Thursday, will we need to know how to work the math for each of the... good question. Okay, so this is for the quiz on Thursday, August 27th, 2020. If you're viewing this video at any time other than August 20th, at any time in the future, and you have a test with me or a quiz, this is for a quiz that is taking place on August 27th, 2020. You will not need a calculator. You may still have math to do, but you will not need a calculator. So the answer will be set in a format if, and there's 2 versions of this test, if there is, so be able to work the math, know how it works, but you don't need a calculator, so I'm not actually going to ask you for a number. So be able to explain how the math works or why the math is important is basically probably the best answer to this. So yeah, those definitely are fair game, but you don't need a calculator. So understand the why of the math, not the actual doing of the math. Okay, there was one other question in the discussion boards, and that had to do with the replication crisis. So the replication crisis is this idea that in certain disciplines, this is a lot more so in kind of the medicine and psychology. Psychology is in kind of a world of hurt a little bit with this. And SciShow has a couple of really good, I think it's SciShow Psychology, has a couple of really good episodes on this. And that is that for science to do as science normally does, someone does some research and they publish it. And then ideally, somebody else looks at their research, looks at the method section, and literally does the exact study over again. And the reason why is that typically, when you do a study, obviously, freak accidents could happen. You could get results that are just a dumb luck. And so there's no way to make sure that it could never, ever be not dumb luck. But what you can do is you can run statistics to see what the chances of your results being dumb luck are. And typically speaking, if it's 95% chance that it's not dumb luck, that you really saw what you really saw, and it wasn't just you happened to draw that kind of, lot out, that's good enough to publish. That means 5% of studies, though, oh boy, there could be some issues. And it's probably not really 5%. I mean, 5% would be a ton. That would be a ludicrously large amount. Well, the way you fix that, and the way science is supposed to work, is that somebody does the exact same study over again. Well, now all of a sudden, the chances of seeing what you're seeing because of dumb luck is 5% of 5%. That drops it down a lot. And, maybe they won't do exactly the same study, but they'll do enough of a study that you can check your work. Well, scientific studies are getting expensive. And going up and asking for money to do something that's already been done is kind of a hard task to do. People want to spend money on new and exciting things. Just like it's fairly straightforward for colleges to get money to build a new building, but if they want to renovate and remodel an old building, that's harder, even though it might actually be a more efficient or better use of the money. So in this case, or even maintenance, good luck with maintenance. So in this case, it's a less glamorous way of doing it, so we don't do enough of it. And there's been a couple of cases where an important study that's really impacted the way that science has been done within a small discipline should have been checked. And it's been 10, 20 years, and no one actually bothered to replicate it because, hey, this was a good study. I'm going to do something cool and exciting, or I couldn't get money to do it. I wanted to, but I just couldn't get money. And then finally someone's able to, and all of a sudden it's like, oh, this is awkward. Yeah, I didn't get the same result. Oops. And so the fear is that we're not replicating enough studies. Of course, the solution is throw money at it, which, of course, there's not infinite amounts of money. It would be great if we could just throw all the money at problems, but, we can't. So that's kind of the concern, that we're not replicating enough. And it's usually called the replication crisis. I think crisis is probably way too dramatic of a term for this, but it's definitely a way of expressing that we have an issue we need to address. Okay, next question. Also from an ISI student, or the physical science student. Is okay to join your office Tuesday? I don't actually have office hours tomorrow. Yes, of course. Okay, so for my students, you've got a link to my online office hours that are on WebEx. Yeah, of course. Yeah, you can always jump in. There may be an announcement coming fairly soon on that one because I'm subbing in for somebody, so the hours are going to shift just a little bit from the morning. Dimensional analysis. Okay, so this is something as a chemist I use a ton, and it's a really important kind of useful one. And I'm going to switch over views to Word, which is probably an absolutely terrible program to use this, but it's kind of my scratch pad for this, guys. So I'm going to transition over here. And I don't think I'm going to talk about Bloom's taxonomy today. but I had that just in case there were no questions. Okay, dimensional analysis. So what you're going to do with dimensional analysis is this is a way of using the units to guide you. And I like to use density as an example because everyone knows what density is. It's the mass of the unit divided by its volume. And so a dense unit is a heavy feeling unit, or a dense thing is a heavy feeling thing. So lead is dense, feathers is low density. There's the amount of volume a pound of feathers takes up is a lot. The amount of volume a pound of lead takes up is shockingly little. Okay, so let's say I want to convert something, and I'm going to say I have 2.3 grams of lead. Chemical formula for lead is Pb. Now, I want to find the volume of that. So what I would do is I'm going to do dimensional analysis. So this is now an equation, and I'm going to set up a fraction. And the numerator of the fraction is going to be the new unit I want. Now, I can do this in multiple steps. This can actually get a lot more complicated than I'm showing you, but it's the same basic thing. Just repeat it. So what I'm going to do is I'm going to look up the density of lead. And I know, it just happens to be I used it today. That's why I know. Density of lead is 11.3 grams per milliliter. By the way, we capitalized the L in liter, so it doesn't look like a 1. In Europe, they make kind of a squiggly thing that I don't know how to make on the computer. Okay, so I know that the density of lead is 11.3 grams per milliliter. Now, that grams per milliliter is its compound unit, but I can rephrase that as 11.3 grams lead divided by 1 milliliter lead. So this is now a conversion factor, and I've got this conversion factor, so that would be 1 fraction. But I have a choice. I could invert that, because this equals that is what I'm saying. So in reality, what I'm saying is 11.3 grams of lead equals 1 milliliter of lead. But I'm expressing that in a fraction. Well, if I take the same thing and put it over itself, that's 1. Okay, so I've got that guy, and then I can simply invert it. So what I can do is I can take one of these, and I would go for this one. And I can say, okay, for every milliliter of lead, I have 11.3 grams. So now I'm going to work this out. This works a lot better if you can actually draw a good fraction bar. So Word is not necessarily the best program for this. So if I take 2.3 grams lead, times that by a fraction. Now, when you times a fraction, you multiply the numerator and divide the denominator. So that would be the 2.3 grams lead times the milliliter of lead divided by the density of the lead. So the 11.3 grams. Well, the grams here cancel with the grams here. So both sides cancel. So now I'm left with milliliters. And what this does, the real power here, is that this canceling tells me that what I need to do is divide by the density. I don't have to memorize to go from mass to volume, I divide. What it does is it allows the units to guide how I do my calculation. And this shows me, the units guide me into setting up the equation correctly. So dimensional analysis is all about using the units to work out what your equation looks like, and thus allowing them to cancel off and giving you a number. And this can become much more complicated quite often, 5 or 6 steps, fairly straightforward in this one, by just simply adding conversion factor after conversion factor after conversion factor. And you can do that. I'm not going to show that at this time, but you can. Okay, so let me transition back to the normal view and pop back on YouTube, see if we got any question. No, so that's about it for questions. So yeah, hope that was helpful for everyone. Actually, I am going to jump into that Bloom's taxonomy, and then if there's no more questions posted, I'll call it a day for the live stream. So let me transition back to the Word document. And so Bloom's taxonomy, Bloom is an educational researcher. So this is, at this point, has nothing to do with chemistry. But I find this is to be a useful thing to understand when you're thinking about classes, definitely from an educator's point of view, but also from a student's point of view. So Bloom's taxonomy is this idea that you learn from kind of the bottom up. There's this kind of foundational level, and I would actually argue there's kind of like a sub-foundation here, but I won't get into that. But you have this foundational level of knowledge. This is basically random facts. You know, the sky is blue, Macintosh apples are red, that kind of thing. Not necessarily random, but they're the facts within whatever you're studying. So in chemistry, that might be like lead is heavy. Lead's density is 11.3 grams. Density is mass divided by volume. Fairly straightforward things. But once you know that, you've gained a level of understanding, but it's not that much. I mean, arguably a parrot can repeat this kind of information. So to understand it more, then that moves up. So once you've got these basic facts downloaded into your brain, then you can start comprehending them. Okay, what does it mean that density is mass divided by volume? How does that relate to the world? Starting to get a comprehension of what's going on. And by the way, you will see a couple of different forms of this. As you start to grasp comprehension there, then you can start applying the material. So, okay, so I know density is mass times volume. If I know mass, now I can know volume. Then moving up, you've got analysis, synthesis, and evaluation. And in this case, you will sometimes see this split apart into different categories. So analysis is, now that I'm starting to think about the material more, I can start analyzing, say, a mathematical problem. Does it flow? Does it do the dimensional analysis thing? Can I use density to create a new concept? Can I rearrange them? That's what you're doing with the concept maps. Can you make the material and rearrange it into something new? And that really requires you to think more about that. It helps you to learn more about the material, but it also shows that you have a better understanding. So these are kind of lower thinking. This is basically memorization, where up here is much more higher level cognitive function. And typically we do better higher up, although it's more work and it's harder. Evaluation would be, like, does this make sense? Kind of critique something. So as an educator, if I'm writing a test, which is never my favorite part of my job, it's better than grading. But when I'm low down, these are going to be fairly straightforward questions. What is this? What is the symbol for lead? That kind of stuff. And multiple choice work beautiful for knowledge. Comprehension, you can start doing some of that. Application, most of your math problems, solve for this. You're going to use what you know, you're going to apply it, and you're going to solve for a question. These are fairly straightforward to write questions about, and they're very objective, which I like. I don't like subjective stuff. Above here, though, these are deeper questions. These are going to be harder questions. For some of my tests, I'll actually put these questions in front, and I'll actually say, okay, these are the level 1 questions, and they're going to be much more knowledge application based, or much more knowledge based. These are level 2. These are going to be much more application analysis based. And then level 3, these are going to be much more synthesis evaluation, where you're trying to okay, what's going on with this scenario? How is this interacting with this? Or I'm going to take what I know and I'm going to reconfigure it into a new thing, something that now exists. And you will see that these 3, they get shuffled around. Some places will actually just put all 3 right on a plane. This, I think, is the older one. Sometimes you'll switch evaluation synthesis. So this varies. For any of my students who are going on into education careers, you're going to see this a bunch and probably be thoroughly sick of it and know way more than this than I do. But it's useful to think about when you're thinking about the way you're thinking, or metacognition. Do you grasp something at this kind of knowledge level, or does it, higher up? And then how are you thinking about it? Chemistry is notoriously, quote, hard in many respects because we have a lot of application, a lot of analysis. And while there's a lot of knowledge, we focus much more towards the middle. Whereas other classes that are, traditionally not so hard are much more down towards the knowledge and comprehension side of things. So yeah, that's a brief introduction to Bloom's taxonomy. Useful to thinking about tests, thinking about what your test question is really trying to get to, which of course is important if you're the one writing the things. So with that said, I'm going to look briefly. Oh, we got another question in the chat. Would you recommend a good foundation or starting point for concept maps? So if I'm setting this up, what I generally recommend is going through your notes. And I think there's actually, for my classes on the learning management system, under like orientation or introduction, there should be a document that says something like concept maps. It'll go through some details. So I'd go through your notes, and the first thing I'd be doing for the concept maps is I'd be taking your notes and sorting them into main ideas, major ideas, supporting ideas, that kind of stuff, which, by the way, that itself is a good study technique. That's something every student should be doing, even if they don't have to do the map. And the maps, I do realize, take a while. So I do apologize for the amount of time they take. I'm going to move my microphone really quick because I can't see the questions. So I would take those, and generally speaking, I would be kind of scattering out the top tier ideas, looking at kind of how they connect a bit, and then kind of branching down a bit for the map. Now, what you don't want to get is a map that's like a tree. Okay, so what you really don't want to get is a map that's like a bunch of grass. So it's like, idea, 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 idea. That's not a concept map. That's sentences. Because when you connect the dots, that makes a sentence. So the next kind of improved concept map is one that's kind of fractal, where it's kind of splitting like a snowflake. So you have an idea, and then it splits off. You have an idea that splits off into other ideas, and they split off into ideas. But where you really get into the awesome maps and really starts making you think, and you start actually seeing things, is where you start looking at them interconnecting with each other. Now, I do realize that usually a lot of the early units that I deal with, things are kind of disjointed. Typically, the first couple of weeks of my classes are kind of this introductory area where things are a little bit disjointed. They're not really getting into the meat of things, and that's in part because there's random stuff we need to cover, but there's also material that is useful. It's helpful for you, but if you missed it, would be slightly less important if you missed it. And there's always kind of the add drop. The first week is always a mess. So a lot of this useful stuff gets moved to the useful but not necessarily core parts of the class, gets moved to the front of the class. That way, if there's issues, that's usually where things go. So if I'm setting this up, I would probably take my main idea, or even call it, hey, module 2 or whatever the core assignment is done. Just kind of stick that in the middle. And then if things just do not connect, just branch them straight off of, module 2 or whatever you're calling your map. That way you've technically connected them, even if they don't connect well. And there's certain things where they connect, but they don't connect. There's no clean connection. They're kind of, existing in tandem. So it would be hard to. And the example is having this SI system connecting to sig figs. And that would be an awkward connection. So I would just start out in the middle, module 2 or module 1, whatever you're doing, and just put that in the middle and just have those branch straight off. And that also makes a good spot where it's like, hey, I can't fit this onto a page. Okay, first page, my major branches, the ones where I know they're not really going to cross-link too much. And then the later pages would all, okay, here's page 2. Page 2 is this thing, that's in the middle, and now that branches off. That's a good way of handling, fluffy stuff or stuff where you just can't get on one page because it would require you to write really, really tiny, etc. Okay, so I hope that helps. So with that said, it's pushing 7:30. So I'll call the live stream a night. Have a wonderful day. If you're one of my students, I will see you this week. If not, have a great time. If you got any questions, feel free to bug me in class if you're a student. If you're not, feel free to post a question on the YouTube comment sections of any particular video. I do check out comments, and we'll put those in the question stream as well. So have a wonderful night. enjoy your day. And this is Dr. T signing off.